Okay, so good afternoon, students. Am I audible to all? Please confirm whether I'm audible to all.
Yes, sir, you are.
Yes, sir.
Okay, so roll number 37 has written that you have not got the mail regarding the meeting link. You are saying?
Yes, sir.
Yes, sir.
What about others?
Yes, sir. Same.
But in my this thing LMS, it is. I mean, in the WebEx meeting app, it is already showing. तो आपको कहाँ से मिला ये link? Like, how did you people join then?
WhatsApp group में से sir.
But someone would have put, right?
Yes, sir. Yes.
मैंने एग्जिस्टिंग लिंक पोस्ट किया था।
Can you please repeat?
अपने अगले लेक्चर पे मैं जो लिंक भेजा था वही सेंड कर दिया था।
Okay, so but this session हमारा हर week होता है the same time, right? So in that particular case, this should have reached you because I have got an email. Let me just log into Cisco once again.
Excuse me, sir.
Yes.
सर मेरा रोल नंबर 35 है तो आज मुझे लिंक नहीं आई थी इसलिए मैं अभी 10-15 मिनट्स N1 बैच में बैठा हुआ था।
Okay, why N1 बैच? आप N2 बैच में हो ना?
हाँ पर सर मुझे N2 की लिंक नहीं आई थी तो मैंने वहाँ फिर मैम की लिंक आई थी N1 बैच से तो मैंने मैम से कंफर्म करा तो फिर मैम ने कहा P2 में हो।
किससे आपने कंफर्म किया था? कौन से नाम से?
जैसे वैसे तो मुझे कंफर्म था कि मैं N2 में हूँ पर लिंक N1 की आई थी, स्वाति मैम की क्लास थी वो, तो फिर मैम ने कहा कि आप नहीं हो N1 बैच में, इसलिए मैं अभी व्हाट्सएप ग्रुप से इस क्लास में ऐड हुआ।
ओके, क्योंकि इसमें तो मुझे दिखा रहा है everyone that 20. Okay, so there is an issue which has happened from 29 onwards it is, right? जो email आप लोगों के पास गया है that is for 21. Okay, I think only one student out of you, roll number 100, is actually receiving the link. Okay. Anyways, I will update this, don't worry. As of now, all of you have joined the meeting. So please inform others also in case anyone is missing.
ओके सर।
कोई अगर missing है तो please inform him also, the student also. I can see only 19 students who have joined. Second. What is the roll number? So all of you, just 2 minutes it will take. I need to generate a list once. Okay, all of you, please check whether you have got any invitation right now from my side, any email.
Yes, sir.
Yeah, so it is an email for the same meeting which we have joined right now. So inform others also in case they have missed or they are waiting for any link. You people can join using that link. Okay, so let us start the session. I believe this is audible to all. We have we'll be doing our experiment, which is experiment number 10 today. Actually, we have completed till our 8th experiment, and ninth experiment is basically binary to gray code conversion. We won't be doing that today because we will be clubbing it with another one. Today we'll be discussing experiment number 10, which is to verify the logic gate operations, to discuss what are the various logic gates, and to use these gates, NAND and NOR gates, as universal gates. Okay, so let me just open the manual for you and we'll discuss from that. Okay, is the manual visible to all?
Yes, sir.
Right, whether it is visible? Okay. Yeah, so this is your experiment number 10, and the aim is to verify truth tables of basic logic gates. And what are the basic logic gates we are going to study here? And or not. 1 second. And use NAND and NOR gates as universal gates. So let us see what is there in the theory portion a bit. So where do we use, first of all, what are these gates, these logic gates, and where do we use them? Can anyone of you answer? Where do we use these logic gates? So a gate is a logic circuit that has one or more inputs and one or more outputs. Now, what are these outputs and inputs doing? So these output and inputs, basically gates are part of digital circuits. So let me just go to here, experiment 10, logic gates.
Sir, your voice is low.
Okay, am I audible to all now?
Yes, sir, it's audible, but it's low.
Okay. We'll try to speak a bit more louder here. So what are basically logic gates? Logic gates are part of digital circuits, and we use these logic gates in order to implement different type of controls in our electronic circuits as well as power electronic circuits. So to develop, or where is the use of these gates? Use is to develop and implement control logic for various electronic applications. Now, why do we call them logic? Because they are working on 1 and 0 logics. And why gates? Because through which we are actually passing the input. So you have just now read here in the manual, what is a gate? A gate is a logic circuit and it has one or more inputs and one or more outputs. The output of this gate will depend upon the set of input conditions. And what are the states which a digital signal has? It has two distinct states, a low and high state. And low is generally represented by 0 and high is represented by 1. So whenever you are having control logic, it will be switching between 0 and 1 are the states, are the logic states. 0 and 1 are the logic states. 0 represents low and 1 represents high. Why do we need this? Why do we need this digital logic circuit? Why do we need 1 and 0? So that your microprocessor or a microcontroller inside your system understands only the inputs in terms of ones and zeros. Whatever your signal is, that has to be converted into a digital signal, and digital signal is represented in terms of zeros and ones in binary form, in hexadecimal form, and so on. So everything is there in terms of ones and zeros only inside your, which is to be read by your microcontroller or your microprocessor. So this logic which we have to make essentially has to be of you can say in the smallest level it is in terms of zeros and ones, and logic gates are used in order to develop and implement this control for various electronic applications. Now, using this gates, we can implement variety of logic circuits that perform a particular task, any specific application. For what is an example? We can implement arithmetic, logic, and control units depending upon our requirements. What are the important gates? So there are 3, 4, 5, 6. So 6 important gates are there which you will study. There are some more, but only these are in your lab. So we will discuss only these specific gates here. The basic gates are the NOT gate, AND gate, and OR gate. Now, what do you understand by NOT gate? I'm sure most of you would have used this type of a gate, or at least developed it, understood, and studied about it in your earlier classes. So what is a NOT gate? NOT gate is something which is negating, or you can say complementing, whatever is your input. So this gate has only one input and it provides one output. And what is the output? Output is nothing but the inversion or negation of your input. So this gate inverts the input at the output. That means if my gate is, let me just draw the symbol here. So the symbol is like this. Whatever the input is coming, I'll have a NOT gate which will invert it. So inversion is represented by this. And if my signal is A, then the inverted signal will be represented by A bar. I'm sure you might have studied this while studying a little bit of Boolean algebra and so on in the first year. In your Tetra also you'll be studying this in your last portion of Tetra. The last unit is digital electronics. So there also you'll study about these gates. So A is your input and A bar is the inversion of that. And when I say inversion, what does that mean? That means if your signal strength is 1 or high, then the output will be just the inversion of that, output will become low. That means this is high and the output will be low here. So NOT gate just complements, or you can say that inverts whatever the input is there. Okay, so when the input is low, the output will be high, and when the input is high, the output will be low. So that is the basic, you can say that operation of a NOT gate. What about the second important gate, which is the AND gate? So this gate has 2 or more inputs and 1 output. That means this AND gate, how is it represented? It is represented like this. So I'll draw in the other case. So first is the NOT gate, and it is represented in this particular fashion, 1 input and 1 output. And what about the truth table? If I ask you to write down the truth table for this particular NOT gate, then if this is A, this is A bar, I told you, right? Inversion is taking place. Then what is the possible values A can take? What are the possible states A can have? And what is the output of this A bar? Okay, so this is input. Yeah. So this is the input and this is the output. Single input and single output system, this NOT gate. That means it is A and A bar. What are the possibilities? One of you has said that the possibility is either it is 1 or whether it is 0. These are the 2 possibilities of A. And if it is 1, the NOT gate will be giving me 0. And if it is 0, the NOT gate will give me an output of 1. So this table which I have formed here, this table is actually known as the truth table. Truth table. Okay, this is very important. Everyone should know what is the truth table for each gate we are going to discuss right now. So truth table, what is it? It is actually telling us what is the output for any given gate, okay, for all possible input combinations. For all possible input combinations. So input, since it's a single input case, let's say the variable is A, then what is the possibilities we know? A can either be 1 or 0. Correspondingly, output we will get 0 and this is the truth table for the first gate, which is NOT gate. The second gate which we have is the AND gate. Okay. The AND gate, how is it represented? It is represented like this, and it is a 2 input or minimum 2 input gate. It can have more than 2 inputs also, but the minimum number of inputs it should have is 2. So let's take one of the inputs, the inputs here as A and B. A is one input and B is second input. Then the output will be nothing but A into B, A product B. We say that this is A and B. What does that mean? What will be the truth table here? So to draw the truth table, we should have A, B and A dot B. So let us see what are the possibilities of the inputs here, because A itself now can be either 0 or 1. Similarly, B also can be either 0 or 1. So similarly, that means A, B will have 4 states, right? 4 outputs, 4 possible outcomes here. So when this is 0, and this is 0, this is 1, this is 1, and 0, 0, 0, 1, 1, 0, and 1, 1. Isn't it? So these are the possibilities. 1, 1. So what is this AND gate actually? What is the logic? The logic is such that when both the inputs are high, then only your output will be high. If any one of the input is low, the output will be low. That is clear? When both inputs are high, both high implies output is high, and if any one is low, then output is low. Then output is low. So 0, 0, 0, 1, 1, 0 and 1, 1. So 0 and 0, you will get the AND gate output will be equal to 0. 0 and 1, the AND gate, since one of them is 0, output will be 0. 1 and 0, since one of them is 0, output will be 0. And 1 and 1, that means both are high, both inputs are high, the output will be high. So this is nothing but the truth table of AND gate. Is it clear to all?
Yes, sir.
Yeah. Now next is the OR gate. So what happens in OR gate? So the OR gate, what is the symbol? The symbol is like this representation. It is also having more than one inputs, minimum 2. So if these are my inputs A and B, okay, and a single output, this will be A or B, and it is represented generally by A plus B. Okay, A plus B, A or B. This is nothing but A and B. This is A or B. So similarly here also we have to draw the truth table. To draw the truth table, again 2 inputs are there. That means 2 inputs can have individually 2 possibilities. So what are they? 0, 0, 0, 1, 1, 0 and 1, 1. Now what is the logic of OR gate? OR, as the name suggests, that it is either or. Either of these 2 inputs, if they are high, the output will be high. Right? That means either input high, then output is high. The output will be high if either of these inputs is high. That means if it is 0, both inputs are low, in that case the output will be low. In all other cases, you can see that one of the inputs at least is high, so the output will be high. Right? So 0, 1, 1, 0, 1, 1. This is the truth table for OR gate. And if you see here, why we represent it as plus, because if we add these two in digital logic, 0 plus 0 is equal to 0. Similarly, 1 plus 1 is equal to 1 in digital logic. Whenever you are saying 1 plus 1, it means that we are having 1 or 1. Okay, plus is representing here OR operation. So 0 or 0, since both are 0, it is 0. 1 plus 1 is equal to 1. Similarly, 1 plus 0, 1 or 0 is 1. 0 or 1 is equal to 1. So for all other possible combinations, you will have 1 other than both are 0. When both are 0, the result will be 0 here for OR operation. I hope this OR operation is also clear to everyone. Next is XOR gate, NAND gate and NOR gate. So XOR gate. What is XOR gate? Who will tell me what is XOR gate? XOR gate is nothing but exclusive OR gate. This is also known as exclusive OR gate. And what is the truth table for this? A, B, and the result is A XOR B. Okay, and what are the possibilities here again? 0 0 0 1, 1 0 1 1, and A XOR B. What is the logic here? The logic here also is that if both inputs are same, having same state, then the output will be low. If the both inputs are differing in states, then output will be high. What does that mean? I'll just write down here. Similar inputs at, we just write in a different way. If both inputs are high, implies output is low, and both inputs different, when I say different states, either 1 or 0 are the states, if both inputs are different states, then output is high. Okay, so this is 0 and 0. Since both the inputs are 0 or low, both inputs are high, are same, we can say are high or low. I can say this is if both inputs are same level, then output is low. If these two are, you can say 0 and 0, both are at the same level, then output should be 0. 0 and 1, here two inputs are there, they are at different levels, 0 and 1, so output will be 1. 1 and 0, both inputs are at different levels, output should be 1, and both inputs are at the same level, 1 and 1, then the output should be low. If both inputs are same level, output is low. If both inputs are different states at different levels, output is high. So this is the truth table for XOR gate. And how does this XOR gate actually look like? XOR gate looks like this. So similar to that of your OR gate, the only difference is that there is another curve here, this one, right? So this is also present in an XOR gate, and it is also having more than one inputs, minimum two. So this is A and this is B. This is A XOR B, and XOR operation is actually represented by this, a plus with a circle around it, A XOR B. So we have written here, that I will tell later. Next is, after XOR we have NAND gate. Okay. So NAND gate is the fifth one. NAND gate. NAND gate is negation of AND gate. So AND gate we have already seen. How is it? This is the AND gate having minimum two inputs. So here also let us say the two inputs are A and B, but the output is having a negation after AND. That means not AND. So if we are connecting it like this will be A NAND B. This logic will be A NAND B. That means we are having, you can understand it in such a way that it is nothing but an AND gate, okay, with a NOT gate after it. Means two inputs are there for the, you can understand this in this particular fashion. This is A and this is B. These two are given input to an AND gate, and after the output of this AND gate, it is passing through a NOT gate. This resultant will be your A NAND. Okay, so negation of whatever you are getting after the AND operation is nothing but NAND gate output. So here also what is the truth table? Two inputs are there, A and B. It will have four possible combinations, and the operation will be A NAND B. What will be A NAND B? 0 0 0 1 1 0 1. So if it is and not, that means 0 and 0, and operation will be 0, not of that will be 1, 0 and 1, and operation will be 0, not of that will be 1, right? This will be 1, 1 and 0, and operation will be 0, not of that will be 1, 1 and 1, and operation of that will be 1, not of that will be 0. So A NAND B will get the truth table as 1 1 1 0. Okay, 1 1 1 0. This is the truth table for NAND gate. I hope that is clear to you. So NAND gate, we can say if we put one inverter at the output of the AND logic, we will get NAND gate. And similarly, NOR gate, which is the last gate, will be if we are putting one inverter at the output of OR gate, we will get a NOR gate. So this is the and this is the NOR gate. This is the NOR gate. So here, if I go to 6, say NOR gate, this is the NOR gate. It is having a NOT after OR. So this is your OR operation. That means minimum two inputs. Let's say this is A and this is B. And if I put a NOT after this, you will get A NOR B. A NOR B. And logic wise, how will this be? So this will be nothing but an OR gate. Whatever the output is coming, cascade it with a NOT gate. So not OR gate, this is OR and this is NOT. And this will be your A and B. This is your output A NOR B. And here also you can develop the truth table. What is the truth table? This is A and B and A NOR B. A NOR B. A, B and A NOR B. 0 0 0 1 1 0 1 1. These are the possible values of A and B, right? These are the four combinations. So A 0 B 0, that means OR operation, what will be the output? 0 and 0, or 0 is 0, not of that will be 1, 0 and 0 or 1, right? One of them is high, it will be high.
0.
So high and not of that will be 0. 1 or 0, you will get 1. 1, if you take the not again, you will get 0. And 1 and 1, you will get 1. Not of that will be 0. So you are getting here 1 0 0 0. For NAND gate you had got 1 1 1 0. So these are the basic logic gates, NOT, AND, OR, XOR, NAND and NOR gates. Okay, so if you want to see in this manual, this is what we have discussed here also. NOT gate, this is how the symbol is, and this is the truth table which we have discussed. And you can see here that these all are coming here, these NOT gate, all these are coming in terms of ICs. What are ICs? IC is nothing but integrated circuits. Integrated circuits. You have studied this in your electrical workshop, integrated circuits. You know? So in that, integrated circuits are nothing but a combination or a collection of various type of devices, small scale, very large scale integration, right? Using that, we are converting these circuits into smaller parts, small elements, and manufacturing a single chip out of it. So for NOT gate, AND gates, similarly for all these gates, we generally have a specific IC which is dedicated to it. So you can see here there is a NOT gate IC which is named 7404. So if you search for this IC 7404, you'll get it is a 14 pin IC. Okay, what are the 14 pins here? This is the portion from here it is starting. There will be a symbol like this here on the left hand side, marking that this is the starting point of pin numbers. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So it is a 14 pin IC, out of which there will be one pin for VCC, which is the supply which this complete integrated circuit requires, power supply it requires, isn't it, to function. So this is VCC, and 7 is nothing but your ground of this particular pin. So between VCC and ground, VCC it will require 5 volt, here it will require ground. So we must provide here 5 volt, and whatever the voltage we are providing it here will be coming out as output. That means the output will be, if we are giving an input of 0, the NOT gate will give you a logic 1. Logic 1 means 5 volt. 5 volt is decided by this VCC value. So depending upon whatever VCC you are giving, the logic level, this 0 means 0 volt, 1 means it will go to this VCC value. VCC is set to 5 volts here. And where is the input given this 0? This 0 logic is given at 1, 3, 5, 9, 11 and 13, because you can see these all are input pins. This is the input pin. What are the input pins here? This 3, 5, 9, 11 and 13. These all are input pins. And what are the output pins? Output pins are these. Output, 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 output. You can see here that this single IC, this single NOT gate consists of how many? 6 NOT gate operations. 6 NOT gates are available in a single IC here, 7404. And these are all independent from each other. That means if you're using the single IC, then individually you can get parallel, at the same time, parallelly 6 NOT operations you can get from a single NOT gate IC. I hope that is clear to all. So similarly here you have for AND gate symbol as well as truth table you have already studied. Here there is another IC dedicated for AND gate logic, which is 7408, and here also you can see it's a 14 pin IC. VCC and ground are there, and since here you require minimum two inputs for AND operation, OR operation also you see. All other logic circuits you will have minimum 2 inputs. So here the number of these gates involved in a single IC will reduce, because two pins are already for the 2 inputs. So total number of pins involved or available are now lesser when compared to the NOT gate. So here you can see 1 and 2 are the inputs. These 2 are inputs and 3 is the output. These 4 and 5 are the inputs, 6 is the output, 9 and 10 are the inputs, 8 is the output, and 12 and 13 are the inputs, 11 is the output. So in this particular case, 7408 has four and 4 independent AND gates. Is this clear to everyone? I hope you are able to understand when I say it's an integrated circuit and 4 such possible IC, 4 such possible gates are there inside this IC. Is it clear? Please confirm once.
Yes, sir.
Yes, sir.
Yes, sir.
Similarly, the next one is the OR gate, or this is the symbol. Truth table also we have seen 0, 111, and or similar to that of AND gate, there is another IC 7432. It is an OR gate IC, and here also there are you can see that minimum 2 inputs are there for for OR operation. So one output. These two are inputs. This is output. These two are inputs. This is output, and 12 and 13 are inputs. 11 is the output. So again, this is also having 4 OR gate. 4 parallel OR gates are possible from this particular single IC. Similarly, for XOR gate, this is the symbol as well as truth table we have seen 0, 1, 1, 0. And here also, since minimum 2 inputs are required, then for a 14-pin IC, we can see that only 1, 2, 3, and 4 outputs are possible. That means 4 XOR gate operations are possible parallelly using this IC 7486. And NAND gate also similarly, the IC is 7400. The truth table is discussed here. We have also discussed, and I can see this 3, 6, 8, and 11. Again, these are the pins at which output is available parallelly for different set of inputs. Input can be at 1 and 2, and output can be taken at 3. Similarly, other two set of inputs can be given at 4 and 5, and output taken at 6. This for NAND, and the last one is the NOR gate. So this is NOR gate. NOR gate, this is a symbol. That means negation of OR gate. That is why the symbol. This is the truth table. We have derived also this truth table. And similar to that of NAND, NOR will also have the 7402. 2 inputs are given here. This input, output, input and input, output. You can see input and input, 10 is output, input and input, 13 is the output. VCC and ground are also given as in other ICs also. So this IC 7402 will have, these two will have 4 NAND gates. This will have 4 NOR gates possible. 4 NOR gates possible here. I hope this is clear to everyone. Using these ICs, we can implement different logic gates. Now, out of these 6 gates, 2 of them are actually known as universal gates. So the NAND and NOR, these are known as universal gates. What are universal gates? These are those gates using which we can develop or we can derive all other possible operations. That means using a NAND gate, I can develop the logic for having NOT operation, AND operation, OR operation. Similarly, using NOR gate itself, only NOR gates, I can implement NOT, AND, and OR operations. So whenever we are able to have such possibilities, okay, we can repeat a specific type of gating logic using another gate. We call that gate as a universal gate. So what are universal gates? It is one which can implement any Boolean function without the need or use of other type of gates. So here NAND and NOR gates are universal gates, and this is an advantage. Why? Because only NAND and NOR gates are economical and easier to fabricate and are basic gates used in IC digital logic families. So the advantage is that if let's say we want to use OR operation, so what will you do? Conventionally, what will you do? Or you'll go and buy one 7432 IC. But in 7432 IC, you can see that there are 4 OR gates. and you don't require these 4 OR gates, you require only one OR gate, but this comes as a complete package. So what you will do, instead of using this, you will try to buy, you can order or buy a NAND gate, set of NAND gates, and using this NAND gates, different NAND gates, you can form the logic of OR gates also. Because it's a universal gate, it will be able to implement the logic of OR operation also. Similarly, the same NAND gate, if we have with us, since it is universal gate, we can implement the logic of AND operation also. In case we don't want to have OR operation, we have changed the logic in our logic design, then we can go for an AND based logic by the same NAND gate, or we can also go for NOT operation using the same NAND logic. So because of this advantage that NAND gate can function as OR and NOT, this type of NAND gate as well as NOR gate, these two are actually called universal gates. Okay, so let us see, by using these NAND and NOR gates, how can we develop these basic logics. So NAND gate, let us prove first, this is the first case of NAND gate as a universal gate. So NAND can be used to make or behave as a NOT gate, AND gate as well as OR gate. Let us see that. So the first one is the NOT operation using NAND gate. So this is the first case, NOT gate using NAND gate. So how will you do? By only using NAND gates. So NOT operation is that if your input is A, okay, your output should be A bar, but you cannot use a NOT gate. You can only use a NAND gate here, right? So what can you do? NAND gate is something like this. It has minimum 2 inputs. So if I connect both the inputs together and connect it to this A, then what will be this? Here also A is there, here also A is there, and NAND gate means A into A, that means A and A, that is A, and not of that. That would be nothing but A naught or A bar. So I can say that this, by connecting the NAND gate in this particular fashion, this is the way we have connected A, that means A is here also, A is here also. So A dot A is A, and not of that will be A bar. The output is nothing but A bar. You are able to operate, or you are able to develop the NOT operation using only this NAND gate, a single NAND gate. You can verify this also using truth table. So this is A, and for NAND operation, you know, A into A, the whole complement. So whatever you are getting, A into A. So 0 into 0 is 0, 0 into 0 is 0, 1 into 1 is 1, 1 into 1 is 1. So this is 0, 0, 1, 1 itself, right? And to get the complement of that, like this, the complement is either represented as A bar or it is also represented as A dash. So complement of that will be this is 0, this will become 1, this is 0, and this is, okay, so this is 1, this is 1, so 1 will become 0, and this is 0, this is 0, then this is basically 1. This is not 0, this is 1 here. So please check this in the lab manual, there should be 1 here. So there should be 1, 1, 0 and 0. That should be the value of output, because input is 0, output should be 1, because then only it will give you NOT operation. Fine. So if I ask you how many NAND gates do you require to implement a NOT operation, NOT logic from a NAND gate, you can say that only one IC, one NAND, not even IC, one NAND gate is required. By giving both the inputs from A itself, we'll be able to get the complement of A. Fine. Now let us see the second possibility here. Second gate which we can implement using NAND, that is AND gate using NAND logic. AND means if you are having two inputs, A and B. A and B using NAND logic. So let us see, we are having this NAND gate with us. Two inputs are A and B. What will be the output? A dot B the whole complement. A and B the whole complement. Now we know whatever the input we give here 2 times, if we are giving the same input, we'll get negation of that. So if we give here the 2 time inputs as A, B bar, here also A, B bar, then whatever the output will be, that will be nothing but A, B. From the previous case, we can see whatever you give here 2 times as the input, output will be nothing but the not of that for a NAND gate. So you can see here AB, here also AB bar, output will be AB bar, the whole bar, which is AB itself. So now check using truth table also. If A is there, B is there, these are the 4 possible combinations, 0, 0, 0, 1, 1, 0, 1, 1. And A, B, the whole complement is how much? 0, 0, 0, complement is 1, here 1, here 1, and here 0. Now the complement of this, again if we take, complement of 1 is 0, 1 is 0, 1 is 0, and 0 is 1. So this is your final value. This is A into B. To multiply these two, you get AND operation, 0, 0, 0, 0, 1 is 0, 1, 0 is 0, 1, 1 is 1. If you compare these two columns, you will get that these are exactly the same. So this verifies your truth table and operation of NAND gate as a AND gate logic. Similarly, the third one also you can implement here. What is the third one? OR logic here. See, this is the OR gate logic using NAND gate. So OR means you should have A plus B. Your input is A and B. So your output should be A plus B. When will that happen? So if you are having two NAND gates here, first AND gate, so A and A are given here, input, you should definitely get A bar. Similarly, B and B are given, this will be B bar. So A bar and B bar, now they are given to the same AND gate. So A bar into B bar, what will you get here? The output will be A bar dot B bar, the whole bar. This will be nothing but A bar plus B bar. A bar plus, sorry, A bar whole bar plus B bar the whole bar. A bar the whole bar is nothing but A plus B bar the whole bar is B. What is this nothing but? This is nothing but OR gate logic. So I have used one theorem here, or law, not theorem, a law here, which is known as De Morgan's law. De Morgan's law. De Morgan's law. What is this De Morgan's law? This De Morgan's law tells us that if I'm having A dot B, A and B, yeah, or A dot B, if I take the whole complement, then I can write down this as A complement plus B complement. Okay, and similarly, if I get A plus B, the whole complement, this can be written as A complement dot B complement, or A bar dot B bar. So I have used the first one here, A bar dot B bar the whole bar. This should be equal to whatever the signal is, bar, plus this signal bar. So what is the signal inside? A bar is the signal, the whole bar, plus B bar is the signal inside, so whole bar. You'll get A bar the whole bar is A, plus B bar the whole bar is B. This logic is nothing but A or B. Let's check the truth table here. For the truth table, you are having 0, 0, 0, 1, 1, 0, 1, 1. And A bar you have found out. If this 0, this will be 1, 1, 0, and 0. Similarly, B bar will be for 0, 1, 1, 0, 0, 1, 1, 0. Right? And A bar dot B bar. What you are getting? A bar, product of these two. the whole bar. So 1 dot 1 is 1, whole complement is 0. 1 dot 0 is 0, whole complement is 1. 0 dot 1 complement is 1. 0 dot 0 is 0, complement is 1. So you are getting here a bar, the whole a bar dot b bar, the whole bar. 0, 1, 1, 1. And what is a plus b? Just add a and b here. 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. And 1 plus 1 is 1. I hope this is clear. So this is OR operation using NAND gate. So how many ICs you require? You can see here for AND operation you require 1 and 2 NAND gates, whereas for OR operation you require 1, 2 and 3. 3 NAND gates for OR operation. So NAND gates, say we are able to form NOT AND or operation. Similarly, the other universal gate is NOR gate. NOR gate as a universal gate. Here also we can form it from NOT logic and OR logic using this NOR gate. How to do this? So the first one here again, A is NOT gate operation using NOR gate. NOR, what is the logic here? If A NOR B, A NOR B. Implies A or B and not of that. So let us see here. If we are having A, since we know we want not operation, right? So that means we have only one input. We have to negate that input. So the input is A. We have to use only NOR gate. So similar to that of your NAND gate, we can give 2 times the same input. Okay. So this NOR gate we are giving here A. Here also we are giving A. Both are the same inputs. Then what will we get? A or A will be A and not of that will be A bar. So we'll get from A bar. That is nothing but this is basically the NOT operation, isn't it? NOT operation. If here it is A, output is A bar, this is nothing but NOT operation using NOR gate. So only one NOR gate we require for implementing NOT logic operation. Similarly, let us implement AND gate using NOR gate, B part. So for getting AND, that means if your inputs are A and B, your output should be AB, A into B, A dot B, A and B. So what can you do for that? A and B. So if you use the first NOR gate and put 2 times A as the input, so A dot A, so A plus A is A, not of that will be A bar. Similarly here, if B is given 2 times, you will get B bar. Now again, these two again should be added here and taken the not off. So A bar plus B bar, the whole complement. That is nothing but, what is this? This is nothing but A bar plus B bar, the whole bar. So here again we are applying De Morgan's rule, second rule. What is the De Morgan's rule? This one. A A plus B the whole bar. Okay, nothing but A bar dot B bar. So here this itself is A. So here what you are getting? So here you are getting A bar plus B bar the whole bar. This is nothing but A bar the whole bar dot B bar the whole bar. A bar the whole bar is A dot B bar the whole bar is just A into B or AND gate operation. So how many ICs you require? 1, 2, 3. 3 NOR ICs, or basically not ICs, 3 NOR gates you require in order to implement AND logic using NOR gate. Similarly, the third one, OR gate using NOR gate. We can implement this. How? Or means again two inputs are there, so A, B, these are the two inputs, and output should be A or B or A plus B. How is it possible? Let's first give A and B both into this. You'll get A plus B the whole bar, and give this 2 times to the same NOR gate. So what will you get? A bar plus A plus B the whole bar plus A plus B the whole bar, the whole negation of the complete value. So that will be again applying De Morgan's rule here. The first case bar plus second case bar, but A plus B bar is the same quantity, right? This A plus B bar, if this is X, then that means this is also X. So X plus S is nothing but X itself, isn't it? In digital logic, we have already seen, right? A plus A is equal to A. That means whatever is there, X plus X should be equal to X. And finally, we have the bar on that. So X is how much? A plus B bar, the whole bar is A plus B bar, the whole bar. This is A plus. So we are getting A plus B from this NOR gate itself. And how many NOR gates we require? Require 2 NOR gates for developing the OR logic. I hope that is clear. So you can see that using the 2 specific gates, NAND and NOR, we are able to generate various logic operations involving NOT, and OR. That is why these are known as universal gates. So that is about this experiment, and to do this experiment as a lab for the record work also, you have 2 options. Either we can do it in the form of a virtual lab. So you can see here there is a virtual lab link, and just open link in the new tab. Also, I'll show you that there is another website, another way you can verify this operation, and there is a YouTube video link also to watch later. Second. So let me just go to that website, this virtual lab platform once to verify. Yeah, so this is the virtual lab link here, and you can go to this is the experiment is verification of and implementation of interpretation of truth table for AND or NAND nor XOR and XNOR gates. XNOR is not in our lab, but this is experiment involving all these. So there is a theory based on all this. Pre-test, procedure, you can go to the procedure, and simulation. So click on the simulation, we'll be opening this options of AND or NOT, NAND nor XOR gates. XNOR is not available, not in our syllabus as of now in the lab. So let's take an example of AND gate. So click on AND gate. You can see that it will open another page. So it's a simulator here to perform AND gate operation. How are you going to do this? You are using AND gate using resistor transistor logic. Okay. So what is AND operation? AND operation we have already seen here. Let's go back here. AND is when 0, 0, 2 inputs are 0, output is 0. Or if any one of the input is, if both the inputs are 1, then only output is 1. Otherwise, all cases output is 0. So when both high, then only output is high. If any one of them is low, output is low. So this is to be verified using this virtual lab setup. So let us see how to implement this. So what you have to do, so what are the instructions? So click on instruction. You will see here that the options which are given are connect the battery. Press the switch 1 for battery to be connected to the circuit. That means connect the battery and connect switch 1. You see I press switch 1 for battery to be connected. So to press switch 1, basically this battery will be connected to the circuit here. That means now supply will reach here to this as well as these 2 points. Now let us go back to instruction. Press switch 2 for input A and switch 3 for input B. So switch 2 and switch 3 are for making inputs high and low. As of now, since this is off, so input is 0. Input is 0. So both logics you can see now are 0. You can understand this as A and this as B. Both are 0 now, and that is why you can see where will you see the result in term of the bulb. This bulb will glow if the logic is high here, or if output is high. So next instruction we can see the switch's on state is this and off state is this. Bulb glows if any one or both the switches are off, and does not glow if both the switches are on. The bulb is in off state like this and on state is in yellow color. Okay, so let me just turn them on and see. So if I'm turning switch S2 on, you can see still the output is 0. So you can say that this is 1, this is 0, A and B correspondingly 1 and 0, the output is still 0. Let me make 0 and 0, 0 and 0 both inputs, output is still 0. And if I make 0 and 1, 0 and 1 again the output is 0. But if I make 1 and 1, let us make 1 and 1, now you can see that output is high. Output is high. So what is this truth table for? If 0 0 output is 0, 0 1 output is 0, 1 0 output is 0, 1 1 output is high. So this is the basically verification of AND logic using this virtual lab platform. Is it clear to everyone?
Yes, sir.
So next also you can go to similarly OR gate, NOT gate and so on. Let me take another example, NAND gate. Okay, so NAND gate, this is the logic here. You can see that the circuit will be differing for all logic gates. So first let us put the battery. So battery is connected and give the supply. As soon as I turn on the supply, you can see that the switch is on. That means even if both the inputs are 0, output is coming out to be high. And that is the case for NAND gate. Let us see NAND gate. Yeah, if both the inputs are 0, output should be high. In fact, output will be high for 3 states and low only for 1 state. Which state? When both inputs are high. So let us see that. So if I turn only one of them on, still output is high. If second one I am turning on only, then also output is high. And if I turn on both, you can see here that the output is low here. So you can see here, this is how the logic is developed and verified with the help of virtual lab. So you can see that we have used, in case you notice, that we have used this control using a resistor transistor logic. So we have used resistors and the supply is reaching here. Whenever this base, we have used a common emitter BJT, okay, and we are using it as a switch. So now whenever this base is high, what will happen? This device will turn on, VC will be 0. VC will be, that means this point will get connected here, isn't it? So even if this point is getting connected here, let's say like this, this is on, yeah, this is on, that means this point is connected here, and whenever this is also on now, okay, that means this point is also connected here. As a result, the current, whatever this battery current is there, that passes through this resistance and through this path, that means no current flows through this bulb. That is why the bulb is low. When will this bulb glow? When voltage will come across it. When will voltage come across this? When both of these are off, these transistors are off. When will they both be off? When both these are actually low. So that, let me make this low, this is low, and this is also low. If any one of them is low, this circuit is incomplete, right? And if both are low, then also the circuit is incomplete here. Then current will flow through the bulb and light it. That is the logic which we have developed for NAND here. So try to do this other portions also, and or not, and NAND nor. And let me see XOR gate also. So you can see the XOR gate is somewhat different. So just click on instructions. Provide the power to the circuit by using power button, and press switch 1 for input A and 2 for input B. So to power the circuit here, let us click on this power button. So when I click on this, you can see that power is being provided to the circuit. That means this 5 volt is given to the circuit. From here it is reaching the base. Okay, that means base for this 5 volt, this transistor Q5 is on, is high. That means this 5 volt gets connected here. But here the base for Q6 is connected to the resistance here, and these two are not connected at all. So output you can see here, still it is 0. The output is 0 here. This is 0. And if this is 5 volt and this is 5 volt, you can see here right now both are 0. This is also 0, this is also 0. So both are same inputs, output is low. What is the XOR? XOR का अगर हम logic देखें, what is that? If both are same inputs, output is 0. Here also both are high, output is 0. Any one of the inputs is different states, output is 1. So we can verify that if both are 0, output is 0, it is off. If both are high, still you can see that output is 0, right? And this green will tell you what is the path of the circuit which is connected. And if any one of them is also on, then output will be high. You can see I have turned off first and turned on second, so output is high. If I do the opposite, still output is high. So this is how you can verify with the help of this transistor logic the input and output of XOR gates. The truth table you can verify. Okay, so this is one way of doing this, using this using the link given here. And another way, let me just tell you, which is not mentioned in the lab manual. Let me just share with you 1 second. So I'm putting here a website. You can see here. Second. Just a second, everyone. Yes, so students, I'm audible to all now?
Yes, sir.
Yeah, so I have opened this website. Is it visible to all? So this is circuitverse.org.
Yes, sir.
Yeah, so here also you can implement various circuits. For example, here this is your AND, okay? So I've clicked on this AND gate. I can place this, and inputs, to provide input, you can provide like this in different ways. So let's say this is your input, and here this is button. If I'm connecting here it as a button. Similarly again, this is also a button, and I want to see output. So output you can go and check here on output panel. So yeah, output you can connect in terms of display also, or whether you want an LED also. So I'm connecting an LED, let's say, as the output. Fine. So if I want to connect the wires here, I'll just have to touch from here and here, from here to here. Just drag it, it will be connected. Similarly here, connect it this particular way, and the output also you can drag it here like this. So it is also connected. Now you can see, if I click on this, this is a button input, okay? So this is becoming 1, okay? So 1 and 0, still output is 0 here. If I make it again 0, hit 1 here, then again the output is 0. For 0 and 0, again the output is 0 itself. If both are 1, at that time, just a second. I think this is 2. Just a second. Let me just delete this and connect it as the output. So both are 0, both are button inputs. So this is 0. This is also. So let me just use the other inputs here. I think it is not configuring the input here as button. So you can take this as the input. This point and this point you can connect. This delete, this is delete, delete, this is to delete. Connect these as the inputs. Similarly, another input here. Okay, so now you can see if this is 1 and this is 1, output is 1. If this is 0, this is 0, output is 0. That means both are 0, output is 0. If any one of them is 1, still output is 0. Here 0, 1, again output is 0. If both are 1, then output is 1. So using this simulator also, circuitverse, you can implement and check different logic gates. Similarly, you have this is AND, this is OR, this is NOT, this is XOR, this is NAND, this is NOR, and this is XNOR. So different other, you can see there are other options also, but our scope is only for logic gates. So you can go and check for these gates also. Is it clear to everyone? So let's say if I take XOR gate here as the input, so can you can take again the inputs. The input is again another input. So this is connected, and this is also connected. Output also you can keep here. you can connect it here. So when both are 1 here input, then output is 0. That means both are high, output is low. And if both are low, then also the output is low. And if one of them is different states, if the inputs are there, then output is high, 1 0 or 0 and 1. For 0 1 also 1, 1 0 is also 1. So this is how it should. You can verify this logic. I hope this is clear to everyone. So I'll just put this. Please confirm this is visible to all as well as understood by everyone.
Yes, sir.
Okay, so
Sir,
this is circuit
it is
bus.
visible.
I have put this. Yeah. So I've put this website also in your chat box. You can use that also. The other link for this is also available on your manual. So you can verify this accordingly. Is it clear to all? So I think that is about our experiment today. You can go through this manual later also. I'll add this manual in your. It is actually available on LMS. I think you all are added on the LMS, right? जहाँ से आप submit करते हैं. So you all can access this manual from there. This is experiment number 10. So in actual hardware, what we are supposed to do, if you are coming to the lab, what we'll do is we'll take these pins, basically these ICs, and connect them on breadboard, and then check the outputs. So also there is one YouTube link. I'm not sure why it is not opening. Let's open it in the other tab. Second. Okay, that video is actually made unavailable. I'm not sure why, but it is not opening. But other than that, you can take this material from this particular manual and complete the record. So what all you have to do for this particular submission? Aim, you have to write down. Apparatus, okay, theory is not required. You have to draw the, this you have to write down truth table as well as the symbol. The gates are not required here. I mean, this ICs are not required. How many gates are there? 6 gates are there, right? Not, and, or,
Yes,
XOR,
sir.
and NOR. Yes, am I audible?
Yes, sir.
Yeah. So what you have to do is you have to just draw the symbols along with the truth table for all these gates. Okay. The ICs are not required here. And then the second part is the verification of these as universal gates. So for NAND and for NAND, you have to show that it is a universal gate. So these 3 truth tables for the operations NOT, and OR you have to draw. Similarly for NOR, show that this is a universal gate by verifying for NOT and OR operations. Okay, so these 3 you have to do and write down conclusion and answer these questions. You can visit this link as I've told to do this for all individual gates separately, and if you want you can verify it using circuit bus also. Also there is one more way of verifying this, that is by using a software which is known as Logisim. Okay, Logisim is also a freeware. It is also available online. You can download that. It is a very small program. Install it, and similar. This is also whatever we are doing here in terms of this online simulator circuit was. There also you will get here in a program. It's a software, small software in which you similarly have AND gate and these inputs and outputs. Just like this, the same you can say same way of representation will be there in that software, which is Logisim. If you want, I can write down in the chat box. Logician. So these are some methods, these are like ways in order how can you verify any truth table or any digital circuit used on logic. Is it clear to all what you have to write down in the record, lab record?
Yes, sir.
Yeah. So that is about this experiment, and in the next week we'll discuss experiment number 9, which is binary to gray code conversion. But it's a smaller experiment, so we'll be clubbing this experiment with another one so that we'll be able to finish the total remaining experiments quickly. Since we have 12 experiments here, right? We may not have enough weeks left for completing all individually. So we may take that next 9th experiment along with another set of experiment. Right? So that is why now you have to complete the record submissions quickly, a bit quicker. Was it clear?
Yes, sir.
Yeah. So fine. The session is over for today. If you have any doubts, you can ask. Otherwise, you people can now leave the meeting.
Thank you, sir.
Okay.